and connect them together. That's a pretty complex process, and that's partly why your FPGA compilations take a long time, because it has to break all the logic functions into simpler blocks. And this is, if you think about it, not easy to do. It has a lot of heuristics to do that. And that's how FPGAs do combinatorial function. But what I didn't talk about is the registers. In an FPGA, the registers are not lumped together as in the previous schematics. You have a register at each LUT output. So every time you have a LUT, you have a register that you can enable or disable inside the FPGA architecture. Okay. So how many inputs should the LUT have? That's a complex question. If the LUT has few inputs, many of them will be needed to implement a complex logic function. We need many LUTs. If you have a big function, we need many LUTs. It will be too big, or it will be slow. Or if it has too many inputs, it will be more costly because each LUT will be more expensive. And a complex logic function could perhaps be broken down into smaller LUTs with better efficiency. So the compromise which is found between the two is to have LUTs which have 4 inputs. That's what you're going to have in your FPGAs. So now another question you have is, how do you connect the LUTs together inside the FPGA? Because it's, I mean, if you think about it, if you have LUTs that you can just solder them together, it's easy. But an FPGA is an involved chip, and you need to find another way to connect them. So you have, what FPGA does is have a programmable interconnect, which is provided what is called switch boxes inside the FPGA. And well, basically it's just similar to a phone network switch box. So inside the FPGA, the switch box is just the microelectronics equivalent of this. And you have many of these switch boxes inside the FPGA. And the design software will just compute all the connections that need to be made into each switch box to connect the local tables of your design together. So now, how can you connect your design with LUTs to the outside world? Well, it's very easy. Some special FPGA cells are connected to this network, and they send the signal to the actual pin on the chip. These cells are called I/O cells, and each physical pin on the FPGA has its dedicated I/O cell, and it's connected to the network. So if you want to connect one LUT output, for example, for putting an LED to the outside world, the LED typically, you just route the output of the LED through all the switch boxes to the I/O cell, and your LED will be connected to the output of the LUT. So why I'm explaining this is because you have to understand how inside the FPGA is working in order to understand your sequence. So as a summary, how it works is that you have a network of 4 LUTs with inside the register inside each of them connected to switch boxes. All the switch boxes of all LUTs are connected together, and sometimes you have I/O cells to interface your design to the outside world, to LEDs or whatever. So, just explaining the build flow of FPGA. So you write the Verilog of the HGL file. So as I showed, this is the Verilog file for level 0, for example. You read them, you compile them, then the logic functions are broken down into LUTs and registers connected together. The output is called the technology map netlist. This is what is done at the phases of logic synthesis and mapping. So LUTs are then assigned physical locations of the chip, because the chip is a network of LUTs, which have no special meaning until you assign one LUT of your design to one location of the chip. This is what is called the place on phase. And then, once you have placed all the LUTs, the design tool will connect the LUTs together to the switch boxes. This is what is called the routing phase. And once everything is done, a binary file called the bitstream is generated, which is a file which is variable by the FPGA device, which contains the contents of each local table and configuration of each switch box. And then, as a binary file, the bitstream is loaded into an FPGA device. So what you have to do to solve the challenge, you have the binary file, which is a closed proprietary format, and you have to understand what it does. So you have to know what is inside each LUT, and you have to know what is inside each switch box, and after that, you can just task. And in order to make this job easier, in the first 3 levels, you will have access to a file which is enabled by the program called FPGA editor. And inside this file, inside this program, you have all the names of the nets. So you can see, if you click on a connection, it will show graphically, and you will see what signal it is. For example, if it's a signal SR, you can see exactly where the SR registers are. You can see the names of the nets. For example, the wire called correct. You can also see where it is routed inside the FPGA. So this will make your job much easier. So I will just introduce you how you do that. So if you download the files, you will have a file called FPGA challenge bin.tar.visit2. To download the file, you can go to the conference website and you have links to download all this. So